Good morning. So we're in day 2 of optimization. So the min means we're finding the minimum values, and there tends to be local minima, and we never know if we're in this one, the global, or maybe this function, who knows, goes out here and turns down, and the minimum is way over there. You never know, unless you have a lot of physical insight into what these things look like. Then I tried to show you the landscape of what minimization in artificial intelligence looks like, and it's a pretty frightening landscape of local minima. The arg part means what we're doing is finding the value of x in our set that gives us the minimum. So x star equals arg min would be this one if we started here, but it tends to be local. Maybe we get stuck in that one. So that's the notation. And then these little plots are the slopes of the function at these points. They're the derivatives. And we see that at local extrema, so local max and local min, the derivative vanishes. So this is a key indicator for us of how to go about finding local minima and maxima, looking for extreme points, places where the derivative vanishes. Then the other cool thing we noticed was that if you're to the right of a minimum, the derivative is positive, pointing you away from it. If you're to the left, the derivative is negative, pointing you away from it. So you need to go in the opposite direction of the derivative in order to converge to the local minimum. And that's, so you can see that from physical examples, and then you also get it from the linear approximation. So you can do it analytically. And this will be helpful to us when x is no longer a scalar and it's a vector. Okay, so this is where we basically left off, and I just wrote down extremely quickly that, yep, it looks like the algorithm is xk plus 1 equals xk, and then you want to go in the opposite direction of the derivative, and then the step size we're not really sure, so we'll just let that be some small positive number. Okay, so that's called gradient descent in one dimension, and it's simply because the gradient is a generalization of the derivative of a function whose values are real numbers. So f here is taking points in R and giving us points in R just like this. So what I thought I'd do, I'd write down the pseudocode, and then we'll do a Julia demonstration. And then we'll extend it to multiple variables. And then we'll have a demonstration by Bruce about how to use this on real interesting applications, not just toy made-up functions, okay? So now the problem with the real ones is that the functions are a little bit complicated, but that's how engineering is. You guys didn't sign up to do an easy job, boring jobs the rest of your lives. You want big, challenging tasks to be faced with, and Bruce will show you one that he's worked on for about 1.5 years now. Something?
It's different. I think this probably for 3 months, and then we need to revise it.
Okay, so he's thinking it's less than 1.5 years. It seems like 9 years of my life I've been working with Bruce on this. So pseudocode, so our stopping criteria will be the derivative equals 0. So we'll start someplace where the derivative is positive or negative, and we want to move to it. So our stopping criteria is the derivative being 0. So that's what we're looking for. It may not be the global minimum, it may be a local, or it could, if we start at a local maximum, we get stuck there. But we can write this as, for example, while the absolute value of df by dx, and I'll write this as our xk is bigger than tolerance. So we should probably initialize it, I didn't leave myself any room, equals x0 equals initial value. Okay? And then if you wanted to make it a true algorithm, you can and we'll put a counter as long as it's less than some k max that we would set. 1e to the 4th or something. Okay, so that means we're going to terminate even if we never meet the condition. So that's the only reason we would do something like that. And then we can update xk equals xk minus f df dx, k equals k plus 1, and then end, and then I realized that I didn't set k equal to 0, did I? Okay. And then it's up to you. You could have an analytical derivative here. So if you've done a lot of calculus and the function is easy, you can do an analytical derivative. But I think you're pretty comfortable now with a numerical approximation. So you could do a forward difference, a backward difference, or my favorite, the symmetric difference, okay? So lots of ways to generate the derivative. Okay. Algorithm seem to make sense? How do you choose S? I'm licking my finger and I'm holding it up and looking at the direction the wind is blowing, okay? So that's a hard tuning parameter. Okay, so choosing S is hard. Once again, that's job security. Okay, so often it has to be quite small. So maybe you have S like 10 to the minus 3. Okay, so it's not uncommon to have to do something like that. Cool. Okay, so let's see, I've already run plots and everything, so, okay, so this is just the usual stuff, using plots, we're using the GR backend. That LaTeXify, I don't know if you've noticed in some of the examples in the book, that's how I generate the tables automatically, the LaTeX, okay, so it'll automatically give you the matrix commands to generate a matrix. And if you don't like the way it's aligned, you can change the centers to R's or lefts and anything you want. And we'll see why I've got random on there. Okay, so here's our first function. This is that less simple cost function that we've been looking at. And let's see. Why is my mouse frozen? Is it showing up here? Yes, that means it's showing up on Zoom too. So we've got local max, local min, well, this is the global in this image anyway, and then we've got a local min here. So I just put the function in exactly as you guys would do a normal function for plotting. X min, X max. Here's my step size, S 0.1. We'll see how that works. H is for my symmetric derivative. I don't know why I even have a delta in there. Oh, I'm using delta for the symmetric derivative. Sorry about that. I remember I was trying something really crazy and I didn't clean up the code. A typical thing. And then what I've got here is a whole bunch of different initial conditions. So I'm going to loop through all of those initial conditions just to see where they end up, okay? So some of them starting over here, 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 close to the local max, et cetera, and just see where they end up. The actual algorithm, there's the while loop. Okay, so if the absolute value of the derivative is bigger than 1e to the minus 5, that's my tolerance, and I'm only doing 1,000 loops, then I'm just doing a gradient descent. And this is an option. Okay. Reset x, I don't really need the xk plus 1. And then I do my symmetric differences and use calling it delta. Okay, bingo. So we'll just run that really quick. Did it run? Oh yeah, so, okay. So here's my output. Ignore the row of zeros on here. So for my different initial conditions, minus 1, 0, etc., these are how many iterations it took. It didn't take very many at all. And this is the value of the derivative. So it all converged quite nicely. And they all converged to either 1.12 or 3.3. So 1.12, we got lucky, that's the global minimum, and 3 something, that's the other local minimum. Okay? Now, here we're kind of fortunate. It's a simple scalar function. Somebody told us to zoom in on this region of the function, and so we could maybe have a few different initial conditions we would think to look at to start it, but normally we don't have this information, or the function has so many dimensions, you can't really do plots to give you any interesting way to start. So if you're going to have local minima, how do you tackle those? So let me write it down and then we'll come back to it. Okay. So simple demo, trivial demo, I should say. Bruce will do a real one. Now, issue we often converge to a local minimum how do we organize our search in order to have a better chance of finding a global minimum? Okay, so that's the, well, when $69,000 was a lot of money, that was the $69,000 question. I guess now it's the $69 billion question. Finding the global minimum. So typically this is what people do, okay? So this is the typical approach. It's called multi-start. Whoops, start. Multi-start. okay? And what that means choose many x zeros and run the algorithm. Okay, so that's good. And then, how do you choose the x zeros? Right, one question begs the next. Okay, fine. I will do multi-start. Well, often people do random search, okay? So, x0, rand, and then you've got some length. How many rows x0 has, let's say m, and then you'll do k. So k equals number of the x zeros. Why random? Because on most problems you don't have a better way to generate it, okay? So now if you have physical insight to the problem and you can bound it because of some reasoning or whatever, you can really get your search area down much smaller. You'll get there a lot more quickly, okay? So the other thing the other approach, we'll talk about this a little bit, is to find a cost function that doesn't have the defect of there's many local minima. It has no local minima and it has only a single global minimum, okay? So it has a single global minimum and no local minima other than, of course, the global one. Okay, and there's a magic word that goes with that, and we'll talk about it a little bit later in the week or by Monday. So it's called convexity. It's a property on functions that makes everything beautiful and nice. Okay. So scalar problems. Here's the algorithm. And very straightforward to implement. Maybe it converges, maybe it doesn't. You tweak. S is at your disposal, and where you start is at your disposal. That's about all you've got going for you, okay? Bingo. Okay, so now what do you do when your cost function depends? So now, our cost function depends, so cost depends on several variables. So Bruce's, yours has how many? 6, that's right. 3 for the rotation matrix, 3 for the translation, okay? Well, the cost depends on several variables. So I want to do it just like we did on the scalar. I want to get some kind of geometric insight by looking at plots, okay? And then we'll do the analytical part to see how it says exactly the same thing. And the whole idea is for some people, they like that geometric intuition, and others, they're more like me, I'm more algebraic, okay? If I see it algebraically, then I'm happy. But everybody's different. Everybody's brain is different. Okay, so image, file. So here, you're going to be a little bit surprised about what I put in. Okay. Bingo. I'm going to shrink it down. I don't need it this big. Okay, so this is a relief map. It's not exactly a topo map because it's already showing it's a 3D aspect, right, of ground. So this has 2 variables, x and y, and then z, okay? And we're trying to find minima. So, bingo. And then let me put in one more. So what's Crazy Grizzle up to? Okay. Yep, get in there. Yep, go back. U, smaller. Okay, I want to see who draws the best topo maps. So here I just want your physical intuition. So what does a derivative mean here? It's the ground slope, okay? And it has, we're doing a gradient because we've got the change in height in the x direction and the change in height in the y direction. So it's a little more complicated than just our bowl and we're looking in, okay? Now, if you're looking at a topo map and you're going, there's nothing much changing here because each of these lines is a constant altitude. So it's constant cost, okay? The cost is constant along there, altitude. We're trying to minimize our cost or maximize our cost, okay? So if you pull out your topo map, typically it doesn't have the 3D relief that's shown over here. What you have is this, just all these lines of constant height. Now, each line is, say, 50 meters difference in height, okay? So there's a fixed amount of difference when they draw the line. So when the lines are really close together, what does that physically mean to you? It's going to be really hard hiking, either up or down, right? It's going to be really steep. So if you were up here and you wanted to head in the direction that's going to get you the quickest to the ground, assuming you're not tripping over roots and all that kind of stuff, do you want to go this way where it's relatively flat, or do you want to go this way where it's super steep? Okay, it's almost a rhetorical question because you know the answer. You want to go down where, if what you're trying to do is to find the local minima, you want to be heading down here to the plains, or if you were trying to maximize and you were on the plains, you are not going to be moving in directions like this because you're staying flat. You're going to be heading up here, and if you want to go the quickest way possible, you will take the steepest direction. So here's the magic. The gradient always points in the direction of maximum increase of your function. okay? So if you were to plot the gradient here, it would be pointing here, where it is the steepest. It's not going to be pointing here where it stays constant. The gradient points in the direction of that. So that's going to be our message. Grad f of x points in the direction of maximum increase of f of x. And I'll remind you that fancy symbol called grad, and it's the first symmetric difference with respect to variable 1, last variable symmetric difference, let's say, and we make it a row vector. That's how it is. So it's just the slopes in each of the x and y in our topo map. But I'm counting on you having had a little bit of outdoor experience, but maybe you grew up in New York City and you never looked at a topo map of New York. That's fine. I'll have to have you go on and look at some YouTube videos for hiking, okay? Now, let's do it on functions. No. Yeah, let's do here. Where'd you go? Okay, that's fine. Okay, so now let's just forget about hiking, okay? That was just another way to get our intuition going. Here's a cost function in two variables, x1 and x2. You can see them curved. Come on, lock yourself down. You can see there's a minimum somewhere. Go away. Here we go. There's a minimum, and the way we would try to get to it is to slide down here towards that minimum. So that's where the negative of the gradient. Now it's hard to picture that. So what are these for the function? These are lines of constant value of the function. They're called contour plots. So this is a contour plot. What is it? It's a topo map for a function. That's all it is, okay? It's just a topo map. Okay, and so what I want to show now is just what the gradient looks like for these types of functions. Yeah, this will do. Where are you going to end up? Come on. There we go. Oh, well, okay. I'll move them back around before I post it. So here's the gradient plotted. Here's the gradient plotted on the contour map. So if it just circles, I mean, no matter where you are, this is going to give, you go normal to the circles, it's got all this symmetry, and that's just because this is really X, this is just they're just circles, there's all this symmetry. Here's a more typical case where it grows much faster in one direction than another. So here, this direction, there's a far distance between the contours, so the gradient would be low, and here the contours are all crunched up, and that's why the gradients are pointing in this direction. So Yeah, get up there, and I'll fix all you guys later. So here's our proposed algorithm. Okay, Bruce, I think I want to go 5 more minutes and then turn it over to you. Here's our proposed algorithm. If we have an xk, we're going to generate a new x. We'll call that xk plus 1 by moving in the opposite direction of the gradient. Now, why is the transpose there? And it's because this is m by 1. And so with the transpose, this is m by 1 as well. The gradient is a row vector. Okay. So to turn it into a column vector, we transpose it. And so this is called gradient descent in the vector case. This is where the name comes from. So this is gradient descent. Okay, so it's being at the side of a big mountain and then heading down the most steepest way to get to the lowest point in the valley. Okay, so this seems like the right thing to do. Okay. Now, using the linear approximation, we can show it's the right thing to do, okay? And I'll do just a few steps of it, and then I'll finish it on Friday, probably. But let's look. Here's our linear approximation about a point K. So this is the Jacobian when f is real valued and it depends upon a vector. Okay, so that's the linear approximation. We seek an xk plus 1 such that f of xk plus 1 is smaller than f of xk. So that's what we're trying to do. We're trying to minimize. You want to find the direction to go to make the function smaller. So I'm going to plug in xk plus 1 here, okay? Just plug in xk plus 1. I'm going to let delta xk then equal xk plus 1 minus xk. So here's when I put k plus 1 and k plus 1, this is delta xk. And so if I have f of xk plus 1 minus f of xk. I want this to be negative. Okay, so that's if and only if the gradient okay, now this is a row vector. I want to choose this such that this row vector times this column vector is negative. And so what I do is not really that amazing at all. I'm going to choose it to be this with a minus s and s positive. Because then, what do I have? Okay, I get a minus s, then I get the gradient transposed, but here's an m vector, here's its transpose, so that product is the norm of the gradient squared. And so this is just equal to minus s norm and so that'll be 0 as long as the gradient is not equal to the 0 vector. Oops. Okay, so I want to give Bruce time to tell his story, but he's going to show you how to use gradient descent, and it's all based upon, come on up, Bruce, and I'm going to unplug. Let's see, you want my adapter, right?
Yep.
Yep.
There's questions in chat that you might want to see.
Okay, I'll start answering them while Bruce is getting set up, and then we may have to deal with some of these on Friday. Okay, could we also treat this as, yep, so that's exactly the first question. Can we treat this as root finding? We'll do that on Friday. Yep, and then we will find a formula for the second derivative, and that's going to be this amazing thing called a Hessian. So, Tribby, if you'll copy those questions in the chat, those are exactly the topics I'm treating on Friday in lecture. So people are thinking in exactly the right direction. So thank you. Stick it in where the button is facing front and then turn the switch on.
Awesome. Thank you.
Is it on?
I think it's on.
Yeah.
Okay, so here.
I don't hear you coming over the speakers. You guys hear them coming over the speakers? No.
No.
Turn it off and then back on. It gets a little. Now talk.
Better now?
Yeah. Okay.
Okay.
I'm going to keep my distance from you.
Sure. So that we don't get caught. Okay. So here I'm going to talk about the optimization and for the real application that we used last summer. And before I dive into the problem, I would like to say something before. It has been in my heart for a long time that I'm so jealous of you guys that you have this awesome textbook. That if I were you, back my time, if I want to learn everything in the textbook, I would probably need to take 10 classes to have all the knowledge I need in this textbook. And so that's the first thing I'm so jealous of you guys. And second is I'm still jealous of you guys that you can meet Jesse every week. Well, twice a week. But for me as a PhD student, I'm Bruce. I'm a PhD student in Jesse's lab. As a PhD student, I need to be independent, so I don't really I cannot really see him that often like you guys. Third thing is I'm jealous of you guys again that I can, that you can learn the things I'm going to present to you. Because back at the time that when I was, Jesse and I was constructing this problem, trying to solve this problem, it was under high pressure because it was last summer. It was 100 degrees Celsius. It was 100 degrees Fahrenheit, 30 degrees Celsius outdoor. And we're doing experiment, and we are facing that we are hitting the limitation of the sensor. And so we gotta do something to solve this. So we need to kind of cooperate with different sensors so that we can use the best of each aspect of the sensors. So that's connect to this problem and why it took us like 3 months trying to figure out the problem, because the accuracy and the precision is important in this process. Because imagine that if I said, oh, that mic is on my left-hand side, but Jesse would say, that's on my right-hand side. Which one's correct? Everyone's correct because it's from different perspective. So we need to find a way that, but if I said, we need to find a way to correctly measure the thing that I say, this thing is perhaps 30 centimeters in front of me. If you say 28, that would probably lead to another, that would lead to incorrect answer, just like this image. All right, and the motivation of this project is this. We try to align, you saw this video before, right? You do this as homework. So that you would say that, oh, the problem is we want to overlay those point cloud back to the image, right? But then you might ask question, why do we need to do that? Is it necessary? Is it cool? Well, and then later on, I'll answer the question, yes, it is necessary for us. First, this is the autonomy experiment that we're doing on a wave field. You can see here that all the point cloud are, so different colors stand for different categories or different semantic meaning of the point cloud. So you can see that the white is the sidewalk, and the green, the light green is the grass, and the dark green is the tree. You can see some walls here are, crisp. So, and then how can we get, so imagine back in like here, when you're doing the problem, that when you see this, there's a pure intensity for the light up point cloud. You don't know the meaning of the points. But here, you can roughly see here, that's a bell tower, right? So you know that's a building. You know you cannot walk there because you hit a wall, right? But how can we assign the semantic information to the point cloud? Then we project the points back to the image. And on the image here, we know, okay, we know those green pixels supposed to be grass. We know those things supposed to be a building. Then we can assign the semantic meaning. We can assign semantic meanings to each point. And now we know what each point stands for.
So Bruce, I'm going to interrupt just a second. So
yep.
At the lower right, you have the actual image coming in from the RealSense camera.
Yep.
That's on Cassie.
Yep.
Okay. So you guys on project 3 are essentially doing machine learning. You're using the same functions that are in neural nets, except you're not really building a neural net, but it's very similar. That top image is processing the camera pixels and then classifying them, whether they are sidewalk, grass, building, bicycle, people, light poles, and things like that. So that's called putting a semantic label. Semantic means words. So it's a word label so that you can reason about what's in the image. No human can do it that fast. So there's a neural network that's been trained to take the camera pixels and produce what looks like a cartoon up there because it doesn't have the fine granularity that your eyes can distinguish, okay? Sorry, Bruce.
Yeah, I should explain more. So like in this experiment, we're just trying to make Cassie, the robot that I'm holding there, while just pushing her, and then we just assign, if you find there's an intersection, make a left turn. If there's no intersection, keep going straight, so that we can go a circle and then go back to a region. All right, that's the autonomy, and that's the experiment that we're that's using the point cloud projected back to the image that we can assign the labels, right? We can assign the semantic meaning of words to the point cloud. And okay, but previously we don't have this thing. We cannot project the points back to the image, so that we only use RGBD camera, where RGBD is just RGB, your regular camera, plus a regular image, where just pixels, and then assign the distance to each pixel. But that thing works. Usually a RGBD camera uses use infrared information, so that if you take this camera outdoor, it's gonna be super bad because sunlight heats everything is super hot, right? So that works up to 5 meters. But you also know that camera has field of view. So imagine probably, so 5 meters plus field of view provides 3 to 5 meters. You can see that. So that now if I want to make a left turn at a corner, I might just imagine I take I just make my eyes like this and try to walk. When I see the corner, I miss the corner. I cannot make a left turn. The corner here is at this corner. That we cannot make a left turn, so that we face that's what I said, that we're hitting the limitation of a sensor. Another benefit of this is you can see on the left-hand side.
So what Bruce was saying there is Cassie doesn't have a head that can turn. So when she's walking forward, all she can see is forward. But if you want to be able to plan to turn left, you have to be able to see far and wide. What happens is the LiDAR, because it's spinning 360 degrees, it's like having eyes all over your head. So if you can take the LiDAR information and merge it with the camera information, then you can see around corners. I mean, a human would be able to see because they can look across. If there's a barrier, the LiDAR can't see through the barrier, okay? So.
Yeah, and also on the left-hand side, without using LiDAR, can see the.
4 minutes.
Okay, then I'll skip this part.
Into the optimization.
Okay, so few things. Okay, so now we are trying to estimate the LiDAR, and so we are trying to project the points. The problem is we try to project the points from the LiDAR to the camera, right? So what do we need? So that's a problem, and that's how we use the rigid body transformation, which is defined as a rotation and translation, a rotation matrix and a translation vector, and then what we are trying to address is the rigid body transformation. So what do we need? We need the features and the camera corners. We need features. All right, I think I'm running out of time, so we'll just dive in. So features are just specific structures in the environment that we could, and then there could be points, edges, or corners. So here, just take the edge detection on the regular image. You can see all the edges are here, and then here's the regular image. And so I'll upload these slides to the GitHub, and then I will show you where the GitHub is. And also the corners that in this project, we'll be using the corners as features, and then to calibrate the sensor in that sense is to project the points, back to the image. So here the problem is we want a cost function. So because the LiDAR features in 3D, you know that there's a points in 3D, and cameras in pixel is a 2D. So we need a projection from the 3D to 2D. So the cost function that just was mentioned is what cost function we need is first we need to project the points, and then we want to align the points. We want to align the points. We want to align the corners with corners. So we need to minimize the distance. So the problem here is project points.
We are measuring the distance in the camera image after the LiDAR points are projected from 3D space onto where the camera would have seen them if you knew the transformation from the LiDAR to the camera. So you pretend that it's the light coming into the camera and you put those points on the camera frame. And now it's 2D and you can just do a standard Euclidean distance, so x squared plus y squared, and that's your error.
Yep, so like here is the pink is the original camera corners, and the green is the projected using the wrong transformation, projected corners. And then now we try to align those two squares. Problem, all right? So now, mathematically speaking, we need to project points, minimize distance. So first, project points, I would take it as a black box for now. How can we project the points? I have an extra slides that are on if you're interested in that, or in the textbook we have that. And then find the distance, Euclidean distance, and then we have all the corners, we're not summing it up. So that's our cost function. Then, using the gradient descent, then we can use a gradient just introduce guys, so that you can use the gradient descent. And we have other method that you will learn in the next class. Is the Bayesian. You can see the difference between the two Bayesian, methods. So live demo. First, you need to download. So you need to download the code from the GitHub. And you need to download the dataset and then put it under the folder and then run this. But why not Julia? Because myself as PhD, I cannot code Julia like you guys efficiently, so I just code in MATLAB. And Julia is the way to go because that's super fast and super efficient, super efficient, not like MATLAB, super slow. So MATLAB.
So Julia runs like Bruce speaks. Fast.
Yes. Okay, so now.
Bruce, you've got 1 minute. Actually, your time just ran out. But,
Okay, just a quick thing. Okay, I just run a demo. So just download it, and then there's only one file here, Robotics 1 optimization. Double click that and run, and hit run. And gradient design, great. Oh, okay, it's gonna take long. Okay, so here you can see it spent 3 seconds, and then it spends 5,000 iterations to solve the problem, and it will pop several things up like this. All right, so this is all so you will pop up 8 figures that everything that in your textbook, you'll pop this up, you can take a look. All right, and then if you want to see if you want to try the Bayesian, where this is great example. If you want to use the Bayesian that you learn next time, then
Raphson applied to the gradient, which to answer the question that was in chat.
Yep, and that's super fast. And if you just need to use this Bayesian, change to 1, and then run again, you'll see super fast. 0.1 seconds, 14 iteration, problem solved. And you pop out the same 8 figures again. All right. So is it an end story? I'm running out of time, but few things to say. How could we represent R? If you dig into the code, you will see the way I represent the rotation matrix is not using the 9 elements that you learned, but I only represent the 3 elements, and then we take skew, exponential map, whatever, and then using the 3, we can output the 9 elements that you are familiar with, the rotation matrix. That's the power of Lie group. That's the power of knowledge. So, I cannot talk now because if I keep talking, it will take a whole semester to explain this concept. And here's the thing I said, the projection map, how can we project the 3D to 2D? Here's the backup slides and our website and YouTube channel. Don't forget to submit that. Don't forget to subscribe to that.
Okay, so hopefully you've motivated them to go and pull down the slides and go through them a little more slowly. But that last part, so we will look at root finding as finding, we will look at optimization as finding points where the gradient vanishes. So it's really a root finding problem on the gradient. And when you do the Jacobian of the gradient, you get the Hessian, and then you get this huge speed up that Bruce showed you from 3 seconds to 0.1, which is important, but also it's a little more accurate as well. Okay, thank you, Bruce.
Cool.